2 incoming at each vertex, and by the way, there's a separation and at least 2 apart, and at least 2 apart. So there are the rules on the secondary structure, on the hydrogen bond. Then let me include also the tertiary structure, and we'll say that, say, maybe this residue, this peptide unit, and this peptide unit are near one another. So then I'll just put in, you know, all those unoriented edges. So the rules, this is for the secondary, I should have used a different color, but I put it down below, so I guess it's cool. For the tertiary is, in fact, they're at least 3 apart. And in fact, there are some coordination constraints on the tertiary, on how many guys you can get nearby. Again, this has been well studied in the literature. And valence, let me just put it this way, valence in this case at most 6. That's the biggest coordination number that you can sort of get for a residue adjunct. X, let's say 8 angstrom or something like that. Okay, so here's a family of graphs. What's the moduli space? I need to say a little more. So consider such a graph. Consider such a gamma. I'm over. Should I? Okay, let me finish. But let me be very quick. Consider such a gamma, and a geochemical. It's a fun word. A geochemical structure on gamma is it's an element of. So let me just write it as A cross X cross Y, where this lives in SO3 valued guys on the oriented edges. So here's the SO3 statistics. And then on the secondary structure edges, I'm going to associate a number, say the Helmholtz free energy of the bond. So there's a real number, so R to the number of secondaries, and it's the energy of the bond. And then a third, actually you can maybe let's make this compact, it's easier, let's make a compact moduli space. Minus some energy minimum 0, and then cross 0, let's say radius max, the number of these tertiary structure bonds. Now this is just going to be distance in angstrom, this is going to be some measure of the chemical strength, and this is as usual an SO3 graph connection. See? What we're going to do is erase edges of, let me just quickly now say, the protein moduli space of length L is, you take the disjoint union, so the set of all geochemical structures, we need a name for it, let me call it delta of gamma, on gamma. So take the disjoint union of all of these guys over all possible gamma, and now identify things where you erase an edge if either the bond is too weak or the distance is too great. Just erase the edge, and it's SO3. And now, as usual, mod out by the diagonal action of SO3, and there it is, protein moduli space. So I'm sorry I ran over. I just want the definition on the board.
So, questions? I think the last space you could maybe have interest. It doesn't matter what he's doing to look simplified, right?
Yeah.
But it's sort of the idea of gluing moduli spaces for all the graphs together into some space. You just may have interest to start with math.
I think so too, and this sort of should be compared with maybe trying to give a cell decomposition based on fact graphs of Dineen-Mumford, where the topological type changes. Now, it's a different story here, but this is in common with that. The topological type of the graph doesn't change. What's that? Anyway, there's plenty more to say, but let me.
Well, no more questions.